All right, so now we can look at the crystal field splitting patterns for tetrahedral complexes. So when we have four identical ligands, this is going to have a point group TD. And we go through a very similar logic as what we did for octahedral complexes. We start out with a free metal ion. This, of course, is just an atom, so you have 5 d orbitals that are all the same energy. And then you do this thought experiment where you put a spherical ligand sphere around the ion, and crystal field theory says that you have electron-electron repulsions between the valence electrons of the ligand and the valence electrons of the metal, and that causes all 5 d orbitals to rise in energy, but they're all the same energy still because of this highly symmetric spherical ligand environment. Only when you impose the TD symmetry, the tetrahedral symmetry, do you get actual splitting of the d orbitals. So how are they going to split? Well, we're going to look up the TD character table, and we see where the 5 d orbital functions lie. Turns out the z squared function and the x squared minus y squared, so the dz squared and the dx squared minus y squared orbitals both transform together as E. And the dxy, dxz, and dyz orbitals are going to transform as T2. So this is very similar to what we saw for octahedral case. Now, there's one difference right now that's worth mentioning that you'll notice, which is that before we're calling them the T2G and the EG orbitals, we don't have G in TD. And the reason for that, G stands for Garada. It means symmetric with respect to inversion. U stands for ungarada. It means anti-symmetric with respect to inversion. This is intricacies of the Mulliken symbols. You don't really need to know about it, but if you're super curious, you can look at the slides from earlier on in the course where I go over Mulliken symbols. That was chapter 4 material. Basically though, the reason why you don't have the G's, the subscript G's in the Mulliken symbols is because tetrahedral symmetry, TD, does not have the inversion operation, okay? Inversion is not present. It's not a symmetry element in TD symmetry. So anyway, now we know that we're gonna have a grouping of 3, the 3 T2s, and we're gonna have a grouping of 2, the 2 E's. And we know which orbitals are which. These are the 2 E's, and these are the 3 T2s. But it turns out that the T2s are going to be higher in energy than the E's. And this is actually the exact flip of what it is for octahedral. Remember, in octahedral, it's the EGs that are higher in energy, and the T2Gs are lower in energy. Here, the T2s are higher in energy, and the E's are lower in energy. So octahedral, we had a splitting pattern of 3 and 2. Here, you're going to have a splitting pattern of 2, then 3. All right, why is this? Well, you can kind of rationalize this by looking at the shapes, okay? These light blue low spheres here represent, valence electrons on ligands, where the ligands are, okay? And so you can see that what happens here is that there's pretty direct interaction for these 3 T2s. They're not really on the lobes, like not as much as the EGs were. If you remember for octahedral, the EGs, let's see if I can find it really quickly. The EGs here, yeah, for the EGs, for dx squared minus y squared and dz squared, you had lobes, directly pointing on the ligands. That was really highly unfavorable. So it really pushed up these EGs. Okay, it's not as severe for tetrahedral, but it is there. Okay, there is a difference. When you look at the x squared minus y squared and dz squared, though, in these cases for tetrahedral, these orbitals, actually these e orbitals, are not really interacting much at all. They're pretty far away compared to the T2s. And so that's why you have more direct interaction between the ligands and the d orbitals here. So that's why these 3 T2s are higher in energy, and why your 2 e orbitals are lower in energy for tetrahedral environment. Okay, so we can write the splitting now. Here are your 2 e's, that's your 2 lower in energy ones, and here are your 3 T2s. Very interesting. It turns out, so same thing, we can call this delta T, okay? And because we know the center line here has to be equal, these 3 T T2s are going to have to go up 0.4 delta T, and these two E's are going to have to go down minus 0.6 delta T. So totally you had these two going down minus 1.2 delta T, and these three going up 1.2 delta T. So net, they cancel out and give you 0. It turns out, though, as we kind of saw pictorially from those images of the interaction, in TD symmetry, the d orbitals just interact less with the ligands, less directly overall than in octahedral. And there's actually a very simple relationship between the magnitude of delta T and the magnitude of delta O when you're talking about the same ligands and the same metals. So if you're just to switch a metal complex that is 6 coordinate and is octahedral symmetry and go to the same metal complex that's 4 coordinate and has tetrahedral symmetry, you will see that the splitting between the E and the T2 in tetrahedral is about 4/9. Actually, rigorously, it should be 4/9, and we'll see why later. 4/9 that of the splitting between the EGs and the T2Gs in octahedral environment. Because of that, you have a very small delta T, okay, for all complexes. And as a result, most TD complexes are high spin, okay? Doesn't even matter if you have a high oxidation state or if you're at a second or third row transition metal. You know, some of these things that would usually fit in octahedral complexes favor a low spin, just by virtue of the less strong interaction and this 4/9 relationship where delta T is so much smaller, that just gives you high spin most of the times. There are some exceptions, but those are really rare, and they're actually tetrahedral complexes that are designed specifically not to be high spin, to be low spin, by using various tricks. So yeah, that's the relationship between tetrahedral symmetry and octahedral symmetry in terms of crystal field theory.